Hi, my name's Chris, and I'm going to talk to you about using FLAME and Oban for ETL. First, I'll give you a little teaser. Who better to quote than Jose? So he was responding to somebody on Twitter and said, you know, without more context, it's hard to say, but in a nutshell, Oban gives you durability, right? So Erlang and OTP, they give you concurrency and distribution. We're all very happy about that here. Oban gives you durability for queues, and FLAME gives you elasticity. Just a quick show of hands, who here knows of or uses Oban? Everyone. Awesome. It's the correct answer. Who here knows of or uses FLAME? Surprising number of people. Is it okay? So I'm going to split it. Who here knows of FLAME? Yes. Who here uses FLAME in production? Yeah, we've got one person. Yeah, I'm going to raise my hand. Okay, cool. So I do think there's something that's starting to coalesce here, and we'll talk about it a little bit more today. But first, I'm going to steal a bit of terminology from Ellie and Pep, who wrote this excellent book, Engineering Elixir Applications. They talk about BEAMOps. And I'm going to twist that a little bit. I'm going to twist their meaning there. They're talking generally about the kind of DevOps mindset when you're dealing with the Beam. I think that that's a really, really interesting and important direction that we need to be going in and discussing as a community. And of course we are. But there's an element here that is starting to open up where we can start to control our infrastructure from within our applications in a new way. And that's what I want to talk about, and that's what I'm really excited about. So who am I, and why should you listen to me? The short answer to that is that you shouldn't, but I'll give you the quick rundown. I'm the CTO of a company called Amplified. We're a knowledge platform for innovation. We use Elixir. We've been using Elixir for 5 years now. We've been around for 7 years. We've been getting progressively more and more like all Elixir all the time. And this is a kind of the next step in that drive. So let's back up in time a little bit. A couple of years ago at ElixirConf in the US, I started talking about what I thought was the future AI stack, why we're betting on an all Elixir future from ETL to deep learning. And this was kind of at the advent of NX. We do a lot of ETL at Amplified, and we'll talk about it more in a bit, but needless to say, that paid off. So last year, I came here and actually was on this stage and talked about how we did a year in production with machine learning on the Beam. And we had some pretty excellent results from that. So we were able to slash Python from our machine learning-driven ETL flows completely. We slashed our monthly AWS spend in half. We had faster bulk loading, which is really important when you've got when you're trying to iterate quickly on machine learning models. And it just works, right? Like, so we get like telemetry, we get you know, all the benefits of the Beam, all the good stuff, right? Super exciting. I was really happy about that. But we can do better, okay? We can do even better than we were. And we'll talk about that today. But first, I'm going to introduce you to Amplified so you get an understanding of what the problem is, and we can frame what we're going to discuss a little bit more deeply. I want to talk about the practicalities here. So Amplified is, as I said, a knowledge management or a knowledge platform for innovation, right? What does that mean? In this case, what you're looking at is what we would call a project within Amplified. On the left, you've got the kind of scope of your project, the target, what you're looking for, and typically what we're talking about are patents, right? When we're talking about innovation, talking about knowledge platform for innovation, we're talking about patents. For the most part. There's non-patent literature, scientific literature, that sort of stuff. But this is really, you know, the thing that we are caring about. And what we want to be able to do is find similar prior art. Prior art is a fancy way of saying patents that already exist for the technology that you're trying to invent, right? And you want to be able to very quickly find things that are similar to whatever it is that you're trying to invent, whether that's some new antibiotic delivery method, or it's a new way of making chocolate, whatever it is, you want to find patents that already exist that are similar to that, right? So in order to do that, we have to go and take all 160 million patents in the world and do stuff to them, right? And we have to embed them in a vector representation. We have to be able to search over the various different fields. We have to be able to filter by various different bits of metadata. And that's a bit of a challenge because it comes in this really nasty XML format, right? So just setting aside the machine learning side of things, which I'm really passionate about and which drives a lot of what we do, it's kind of a big data problem, right? We've got 160 million patents. It's something like 7 terabytes. And we get them from a data provider who go and get them from all the different patent offices and put them into this World Intellectual Patent Office, or World Intellectual Property Office organization. Sorry, let me try that again. World Intellectual Property Organization, WIPO, standard. ST36, it's not a very robust standard, let's put it that way. There's some issues with it. Anyway, we want to get the XML and put it into something a little bit more modern, something like JSON, so that we can index it into Elasticsearch alongside some value-added work that we're doing, like the machine learning, right? And it's a lot. So, the weekly updates, we're doing every single patent office in the world. We've got, average volume. Most of these are 4, 5 figures. Some of them are 6 figures. Those are per week, right? And then on top of that, we've got a whole bunch of other updates and things like that. So on average, we're talking single-digit millions that we're working with per week. And it looks like this, right? So we've got the patent offices. They're sending the data, or the data supplier is getting the data from the patent offices, and it's going to our data warehouse, which is a single, very large Postgres instance, which there are technical reasons for that I'm not super excited about, but we'll take that as a confine, or as a rule that we have to work within, right? We always work within confines, and that's one of them. So what do I want to do? I want to get from the data warehouse over there, and I want to do something to the data, and then I want to put it into Elasticsearch, right? Simple. Should be. And, in the end, we're going to be consuming from our application cluster, our end-user application cluster, right? So, and since we already have it, well, the most reasonable thing would be to do something like this, right? Just throw the app cluster in between and have it do the work, right? It's going to read from the data warehouse. It's already getting data from the data warehouse anyway. We have to go there to get certain bits of information, like metadata about loading, stuff like that. So, right, throw it in there, right? But the data is bursty. We don't want to be using the resources that we have for our application. We certainly could have a heterogeneous cluster where we start up different things in our application tree for different nodes. All of that is possible, but I also need GPUs. As I said, it's bursty. I want to be able to scale up and down really rapidly, and I don't really want to do that in my main application. So add a separate ETL app, right? So now we've got the data warehouse. The app cluster is talking to the data warehouse. We've got this ETL cluster that's running and doing all the work and sending the data to Elasticsearch. Cool. It runs on AWS. It scales independently. But one thing is we have to have a way of getting the processes, the work that's being done to the ETL cluster. So that ETL cluster is basically taking every updated patent or new patent and running it through our ETL pipeline, right? And that pipeline basically goes and it parses the XML, it runs some machine learning, it embeds the patent, and gets it into the format that I showed you before, where it's going to go into Elasticsearch, right? So we'll add an event bus, right? So we've got RabbitMQ that's going to act as a queue. So we've got our app cluster, which is reading from the data warehouse and learning about the updates. Now, the app cluster is doing that because it's already working with an application database. The ETL cluster, I didn't want to give it its own application database because I want it to be able to live independently off in its own world and scale really rapidly and scale really, really wide. So it's living off on its own in AWS land. The app cluster is living on Fly. The data warehouse is living in AWS. The Elasticsearch is living in AWS. And now the app cluster is going and getting the updates from the data warehouse and feeding them into RabbitMQ, which the ETL cluster running Broadway is pulling from, right? And Broadway has this staged, back-pressured pipeline built on Gen stage, all good, okay? Yeah, this worked for a bit. So, some challenges. Right. I've already alluded to this. The first one that we kind of run into is horizontal scaling, right? There are some different ways that we could scale horizontally. I really wanted to be able to scale down to 0, right? Because it's bursty. Weekends, we're not getting any updates throughout the day. Usually, updates are running during US working hours, right? So we could be getting 500,000 at 12 p.m. on a Tuesday and 0 at 12 a.m., right? So there are ways of dealing with this. We can check the queue length. We can scale the number of machines that we have based on the queue length. None of them are particularly attractive. We've got a lot of ways of doing it, but it's, as I said, very, very elastic. And we might want to just go really, really crazy wide because we want to do a full rerun of all of the data, right? Like maybe we want to embed everything. So we want to go crazy wide, and all of a sudden we've got 160 million things in the queue, right? Or we need to fix some piece of some piece of data, right? So let's say that we realize that we've made a mistake in the way that we calculate the priority dates for a patent. We need to go and fix all of those. All of a sudden, we need to enqueue 160 million jobs. Now, they're only going to run and fix a certain part of the patent, but still, 160 million jobs, right? Like, we're going to need to scale that out. It's not going to. It's something that needs to be done relatively quickly. The other aspect here that we have to consider is vertical scaling, right? So we need to right-size our work so that we're not wasting cost. This means that we're going to be managing a heterogeneous cluster. We've got GPUs for embedding and for a few other machine learning tasks that we're doing. And the CPU size is going to differ depending on the type of work that we're doing. So like the example I gave you before, OK, we want to recalculate the priority dates. All right, that's not going to take a great deal of work. Now, if we want to run and work on the entire patent, right, to churn through that really effectively, we need to give it a little bit more power, maybe a little bit more memory. Maybe we want to work in larger chunk sizes, right? And we can try to manipulate these things to maximize the throughput. But yeah, we needed to be able to vertically scale and consider those things. So the other aspect here is code sharing and duplication. Now, we're deploying in different places. We went down the road of an umbrella app. I wouldn't do that again. And in fact, we'll come back to this later, but kind of one of the lessons learned here is actually a lot of this is achievable without necessarily using something like Flame, but I'll talk about that later. But the thing to think about here is that we needed to be able to share code between this application running on AWS and this other application running on Fly that are doing very different things, and they need to be able to, we want to minimize the surface area. We want to be able to share testing. We want to be able to share all that good stuff. Okay. Scheduling and orchestration. So when you're working with Elasticsearch and you're working with like a large like search index, you need to be able to do things like force merges, which is basically a way of taking an index which gets fragmented over time and forcing it down into sometimes a single shard or a single index, basically. This is really important for approximate nearest neighbors if you're doing any kind of vector search in Elasticsearch. It runs much faster if it only has to traverse a single graph as opposed to trying to break up those graphs. So we wanted to be able to schedule this so that we could pause the queues and go and run this force merge. And it takes often like a day to do a full force merge. So we wanted to be able to kind of orchestrate this and schedule this. Now, on top of that, there's the consideration of what you're doing with hardware elsewhere as well, right? So let's say that you've got a whole bunch of machine learning jobs. Maybe those are working with an API service somewhere else that's spinning up a number of GPUs. You want to be able to maximize your utilization of those GPUs, and you don't want to waste them being online, right? So if you are auto-scaling elsewhere, and you are running this kind of very bursty ETL job, that ETL job may only sometimes need to call to the very expensive GPU job, and what it will do is it will wake up those GPUs elsewhere in order to get a single or two responses, and then they'll idle out and go back to sleep. So one of the things that we wanted to be able to do was to collect throughout the day these kind of very expensive jobs and have them all run at once so that we're able to maximize the throughput through our GPU cluster elsewhere. So retries were a thing that was kind of painful. So I don't know who here works with RabbitMQ, because I love RabbitMQ. I think it's great. Yeah, working with dead letter queues ends up being a little bit painful when you're trying to when you want to be able to retry, back off, that sort of stuff. Basically we had to go in and check the dead letter queue and flush it out back into the queue, see if anything was going on there. It made it difficult to figure out what was going on in terms of mistakes or errors in our pipeline as well, until we went and reran them again. A little bit of an issue. So the infrastructure complexity, I think, goes without saying here, that we're adding additional services, we're adding additional infrastructure code that we're writing in order to figure out when and how we're going to scale, right? We're also then supporting an additional service with RabbitMQ, which is really, really easy and really excellent out of the box, but does take a little bit of management and a little bit of work. Now, we're a tiny team, right? We have 2 developers. It's me and one other guy. And so, a lot of the benefits that we have seen that I discussed in other talks and all of that, they start to be diminished when I have to start managing additional services, and I have to start thinking about where my brain share is going and how much I'm thinking about RabbitMQ, how much I'm thinking about deploying to AWS, how much I'm thinking about the ways that we're going to do auto-scaling on AWS versus auto-scaling on Fly versus whatever else that we're doing. So it's adding up, right, this infrastructure complexity. And then the last bit is just maximizing throughput. Who here has used Broadway in anger? I wish it was more. There's 4 of you. Broadway is amazing. It's a really fantastic library, but it can be really tough to figure out how to maximize throughput when you're working with it, right? So it's gen stage. You're basically doing process-based scaling, and so you're saying, okay, well, I want to be able to pull this many off of the queue at any given time, and you're trying to balance that against like your memory requirements and then how many you can feed through to the next stage. But this is all happening on a single instance, right? It's not sharded across multiple machines. It's sharding across processes. So it can be challenging to figure out how to maximize throughput, right? And generally, when you're working with this sort of stuff that can have wildly different hardware requirements, it's a bit of a square peg round hole problem to be trying to scale it with the number of processes that you're running instead of scaling it with the hardware that you're using, right? So problems, difficulties, challenges, but it was working really well. I was really happy with it. It was kind of plugging away, and it was much better than the previous iteration, which was a mix of Python and orchestrators and all sorts of terrible stuff. And then all of a sudden, this guy showed up on my screen. Let's see if it'll play. There we go.
Hey, it's Chris McCord, and today I want to show off FLAME, which is a library and programming pattern for elastically scaling parts of your application without doing a bunch of rewrites, without having to adopt all this functions as a service, serverless complexity.
All right. So that guy, he shows up on my screen and starts talking about this very silly acronym. FLAME, Fleeting Lambda Application for Modular Execution. You've really got to you got to get it, like, we've got to have the fire and the Phoenix references and the flame and all that stuff. Yes, okay. But it's an absolutely fantastic thing. It's a pattern, I think, which is one of the things that's emphasized in the README. This is kind of just stolen from the README here. But the idea is, imagine if you could auto-scale simply by wrapping in any existing app code in a function and have that block of code run in a temporary copy of the app. So with FLAME, you've got your entire application is the Lambda, right? You're not going and building, you're not doing, gateways over here and having to upload your code to S3 in order to use like a kneecapped version of Node and all this stuff, right? Like, you're not doing any of that stuff. You're just taking your application and you're just sending it and just running it. It's already there. Now, this kind of feeds back to what I was saying before about, could I have done this a different way? Or could I have done this, without FLAME? Maybe, In fact, when I was re-architecting in order to use FLAME, that's when I started doing things like, oh, I can just config my application startup in such that I dynamically choose which children are going to start. And I'm like, oh, I absolutely could have done certain components or certain aspects of this just by starting up different parts of my supervision tree. Sometimes things are obvious in hindsight. But let's have a look at how FLAME works, right? So you start your FLAME pool as a child in your supervision tree. You config it there, kind of what we're all quite used to. It's a process. And we give it a name. We tell it which backend we want to use. We tell it how many copies we want to have running at a minimum and a maximum at any given point in time, so how big the pool can get. How the concurrency, so basically how many processes can be running on each member or each flame in the pool, how long to shut down. There's a few other config options here as well, but it's beautiful, it's simple. There's a Kubernetes backend as well, so it's not just for if you're on Fly, if you're using Kubernetes, you can join the party as well. And here's the example from the README, right? And the only real difference that you're going to see in this function is that there's a wrap around the main body of the function that just says flame call, right? And we tell it which pool we want to use, and then we just give it a closure, basically. Say, here, go, do something. And what's it going to do? It's just going to use our basic OTP primitives, right? Jason Steves had a really great talk at ElixirConf US in which he kind of explained how this came to be and was just like, anybody can do it. Anybody could do this. It's really, really simple. It's brilliant, but it's simple. And so you provision a runner, you go and you're calling the Fly Machines API, but you could be provisioning that from Kubernetes if you wanted to. It connects, right? Once it's connected, then we're going to send the function, which is that bit in green for execution. It's going to return the result back to the remote parent caller, and then it just idles down. All right, that's pretty simple. That's pretty great. I got really excited about pools. I was okay. So FLAME pools, we can configure different pools for different types of hardware that we might want to use. So that issue that I was saying about vertical scaling before, all of a sudden, I've got a solution for it. And so after watching the talk and looking at it and all that, I started thinking, all right, we're already using Fly. We're already heavy Oban users for all the good reasons that everyone here is using it. Yeah, all right. Forget the infrastructure as code. Forget writing more, JSON DSL. I'm going to use FLAME. and I'm going to use the primitives that I already have in Elixir. When I think about scaling queues and I think about concurrent work, which is what a lot of this ETL processing is, there's a language and a whole ecosystem that we use, right? Like there's the whole Beam ecosystem that we use for concurrency and for dealing with concurrency in really interesting ways. And I was just like, well, what if I can start using that to actually orchestrate my hardware rather than just the other way around? And so I started moving in that direction, right? I started thinking, wait a second, okay, Oban. Now, everyone here is using Oban. I have basically stolen from their README here, and I'm not going to go through it all, but we're going to come back to a couple of these points, so I want to hit on them really quickly. But if you're not familiar with Oban, it is job orchestration done via queues. It's reliable, it's consistent, it's observable, and it absolutely delivers on every single one of those promises. You have a whole bunch of transactional control, you get your database backups, you get fewer dependencies. But the main thing here that I wanted to think about is queues, right? You get isolated queues, you can control those queues, you can start them, stop them, and you can do all this via code, right? Like you can have Oban queues, or Oban workers saying to Oban to stop the queue until something happens. It all starts to collapse in on itself in a really beautiful way. The queues are resilient, which I had some issues with data loss in RabbitMQ, which probably was my fault, but we have like job canceling, we have triggered execution, which is really awesome. The jobs can be unique, which was a big problem that we had dealing with RabbitMQ. We can schedule jobs. We can have periodic cron jobs. We can set job priority, which is really, really useful. Metrics, node metrics, graceful shutdown, and telemetry integration. So yeah, it's everything that I want, right? But at its core, it's basically this, right? You have Postgres, and on top of Postgres, we have a number of different queues, and each of those queues has jobs, right? Simple, easy. Queues. It makes me excited. I'm happy. So these are actual queues from our application. Now let's talk about how we re-architected things and rewrote what we were doing in Oban with Flame. Right? So everything starts from a run, right? And this is actually using a cron. So every 15 minutes this runs. I apologize because there's some mangling that went on, but I think it's mostly very readable. It should be fine. We go and get the old load ID, which is basically how we determine what's been updated. We go and we check what the latest run was. We see where we're at, and we determine which jobs we need to, or which patents we need to in-queue effectively, right? Every 15 minutes. And then this is kind of buried within that run function we've got in queue publications. It's really, really simple. We're taking that minimum load ID, the maximum load ID, going and get all the publication IDs, which are how we identify the patents, and we just in-queue them. We just do worker new and insert all, right? Just wait. So we've got Oban doing part 1, right? Now it's doing it's adding upsert. It's saying this is a job type for upsert, and we can differentiate the work that we're going to do based on the different arguments that we're going to pass on to our worker, right? Tell it the publication ID, the modified load ID, and we go and then pull off of that queue. So now we've got the perform function for the upserts, and what you're going to see here is that we've got a wrap of the Flame call here, and we're going to go and throw those to the ETL runner. And it's as simple as that. All of a sudden, my Oban job is running on another machine. I'm not running it. I don't have to worry about like queues going to specific nodes. I don't have to worry about scaling nodes. I don't have to do any of that stuff. All of a sudden, any Oban job that I have can just run on whatever hardware I want. And I mean, it's true of any function, right? But it feels particularly powerful in the context of Oban. So, we go and we get the existing publication, we transform and we upsert it, we do just really simple work, right? All this code is being shared. Excellent. So the transform and upsert, we go and we transform the XML, we maybe insert a new family member job. I'll return to that in a moment. We stage the upsert and we send it away. So coming back to what I was saying before about those forced merges and saying how we have problems with scheduling and stopping queues and stuff like that. Like I said before, Oban can be controlled with Oban, right? I mean, it goes without saying. But you have this ability to basically say, OK, Oban, I want to pause the queue. Then I want to drain that queue. I'm just going to wait for all those jobs to finish. Then I'm going to go start my forced merge. And I'm going to restart in an hour. And every time in an hour, what I'm going to do is I'm going to run this function, which is just inserting another Oban job. And it's just in an hour, right? So I'm saying I want to schedule it in an hour and insert it. So going back, you can see to perform that scheduled restart, potential restart, all I'm going to do is I'm just going to go and check if the job is completed. So if the force merge is completed, if it is completed, then I'm going to resume my queue. If it's not completed, then I'm going to restart in an hour. Again, it's incredibly simple. It's like 10 lines of code, and I just considering how to orchestrate this with RabbitMQ, with a cluster in AWS. It's a headache, and it's at least a couple of days of work probably. My estimates are beloved by my co-founder, but it's just a couple of lines of code, and basically if you can think it, you can do it, right? And so what does our ETL look like now? I can go and peek at it with Oban Web at any given time. I can see each worker, the ETL worker, I can see each of these jobs that's running. I can go and examine them. And I can go and see that I've got a ton of machines running on fly. So I can go and inspect all of this stuff in a really nice and intuitive way. And I want to compare that to Broadway, which I was really excited about this when I started using it. Broadway dashboard is amazing. It's brilliant. You can see how your GenStage pipeline is running, your Broadway pipeline is running. You can see how many are successful, how many have failed, all of that stuff. But I want to compare it to Oban, where you can see a job that's failed and try to get an understanding of why it's failing. You can see when and how it's meant to be rescheduled. You can see which node it's running on. You can see how long it's been sitting in the queue. You can see, like I said, its current state. All of this introspection is incredibly valuable on a day-to-day basis when I'm going in and trying to figure out what went wrong, why doesn't this data match what I expect it to or how I expect it to look. Why isn't this patent available? What's happened here? All that sort of stuff. And I start getting complaints from AppSignal, or we used to use Sentry, coming through from this. I can go and pin it down. I can go and find the job. I can do a lot, right? One other thing that I can do, I'm just going to point out, is schedule jobs. So I mentioned before about that big GPU cluster, all of that. I mentioned scheduling for orchestration, starting and shutting down the queue. But what else I can do, which I'm really excited about, is the ability to go and scale elsewhere in a responsible way, right? So I can take all of these embeddings, and we can go back to this bit in the code. Hold on, I apologize. Here we go. We were here. No, it's here. Sorry. So in the transform and upsert bit of code that I've got there, I've got transform XML, and that transform XML function conditionally calls whether we should insert a job for embedding. You can also see that it says maybe insert new family member job. So we can kind of span out and change the workflow depending on the code that we're running, depending on the business logic. And when you can start thinking in terms of your business logic rather than having to back out of your Elixir code in order to go and work on your Terraform or your CloudFormation or whatever, it becomes really incredibly powerful. It just works into your function pipelines and into your work, right? And one of the things that it enables is the confidence to build real-time features, right? So at Amplified, as I mentioned, we are a knowledge platform for innovation. One of the things that you might want to do when you're working in Amplified is watch a patent or a family of patents and get an update based on if there are new legal events, if there are new family members, if there are new similar patents. And we want to be able to differentiate from some of our competitors by being able to update the user as it happens, right? As soon as we have that data, as soon as the ETL has processed it, we want to be able to ping them and send them a notification, right? So we have a notification system set up, and this is what our users get now. So, you know, I said here you've got this maybe insert new family member job here. That's what we're looking at here. So we're transforming it, and then we're going to go and we're going to go check. Has there been a change to the family ID? And if so, then we're going to enqueue a job that's going to go and check if anybody has subscribed to that family. And if so, then we're going to send them a notification. Happens in real time. Our customers are getting intelligence earlier than they would in other platforms, simply because of the confidence that we've built in the ability to integrate our ETL pipelines into our application, and we haven't been tied to the hardware requirements of our app, right? We also get a whole bunch of code sharing benefits. So, you know, this is an example of code sharing where we want to exclude certain patents based on, you know, based on their kind codes, and we now just run that in our single monolith, right? So we've got just this code, it's shared, we don't have to worry about dependencies, we don't have to worry about an umbrella. No one should ever have to worry about an umbrella. None of that stuff, it's just there, right? Like, and it's available to the rest of the app. So we've ended up here, right? Not quite so fast. I did do a little something, which is I added a separate embedding service, right? I ripped it out because I didn't want to have to deal with the GPU with that aspect of it. We do use GPU pools for other things, but one of the things that you have to consider here is that large language models and any kind of large machine learning model take time to run and to bring into memory and to get ready for inference. So first on my list of downsides, gotchas, lessons is don't go and try to load a model that you want to run quickly on ephemeral hardware, because when you go and run the ephemeral hardware, you're taking a cost of the time that it takes to load that memory or that model into memory, right? So NX serving is a much better choice. You get a lot for free with NX serving. So if you're into machine learning, that side of things, use NX serving, set up a separate NX serving cluster, deal with it that way. It is significantly slower to insert many jobs into Postgres than it is to send messages to RabbitMQ, even for durable queues, and they can quickly compound. As I showed you, you get excited, like I am, and start forking off a whole bunch of different jobs. And when you do that, all of a sudden your ETL pipeline is producing 3, 4, 5, 6 times as many jobs, and you're trying to insert them quickly, and it can very quickly make your database not happy. So, you know, pay attention to this, pay attention that it takes time, and pay attention to overloading it, which is similarly, if your runners need access to your database, think about your ecto pooling strategy and your general concurrent load. So if you're going very, very wide and all of your nodes or all of your Flame runners are starting up a connection pool to your ecto database, that's going to be bad news really quickly, right? And as I've said a couple of times now, could I have achieved much of this without Flame? Yes, but confidence is so important when we're thinking about architecture and we're thinking about the way that we're going to build our applications. Flame gave me a ton of power and the ability to just write Elixir code instead of going off and writing infrastructure as code. Being able to use the kind of built-in primitives that we have with OTP, you know, streaming works across the cluster, right? You know, sending messages works across the cluster. My runners are starting up, and they're able to actually, some of my jobs actually send messages across PubSub to my application, right? So it's possible to do that, but it's much, much easier to do it with Flame, right? So queues, pools, and we get a ton of flexibility, right? So your different queues, which provide you with one level of abstraction in terms of thinking about controlling your workflows can then be it can then interact with different pools, which give you another level of abstraction for thinking about your workflows and control over your workflows, your maximum number of workers, all that kind of stuff. And you can work these things, you can build these things together such that you get this really powerful combination that allows you to utilize Elixir, allows you to utilize the primitives that we have with OTP to be much more creative and thoughtful in the way that you are architecting your application. And I think that that's kind of a push in the direction of what we can call BEAMOps. There's a lot more to be done. There's a lot more to think about. But I think the more that we can pull the orchestration inside our application, inside the primitives that we have with OTP, the better that we're going to be, and the more that we're going to be able to do creative, unique work that other platforms, other ecosystems can't achieve. So thank you.